All right, welcome back to another lecture from the British Columbia Institute of Technology, Technology Teacher Education 4010 class, where today we're going to take a look at the 7-segment display using some binary numbers, and we'll spend a little bit of time talking about some variable types that you'll see used on the Arduino. And in the process, we'll talk a little bit about hexadecimal too, because it's very important when you're programming to know that dead beef is worth more than a bad babe. That's actual hexadecimal math for you. Anyway, let's start out by taking a look at what the heck is a 7-segment display anyway. You've seen a lot of them. They're going to look really familiar as soon as we get going here, but just go ahead and log into your Tinkercad account, get that all open because we're going to be doing some breadboarding here, and you're going to be able to join along in the fun. And while you open up Tinkercad, I'm just going to swipe some of this off the screen and shrink myself down and hide in the bottom corner down here. There we go. Okay, so let's take a look right in here, and we're just going to start off with our plain Arduino and breadboard in the Tinkercad setup. And in our last video, we're using some text-based coding. We're going to go back to blocks for today, and this is great. So let's get rid of that code for a second, and let's go find ourselves a 7-segment display. Okay, now if you scroll down, you'll see that there's outputs on here. We've got all sorts of interesting things to look at for outputs, but down by the bottom, you'll find a 7-segment display. And there's also the 7-segment clock display, which consists of 4 7-segment displays. But we're going to start out by just displaying one number. So drag that 7-segment display onto your board and put it down here. Now, something like that should work great. Okay, now when you put this board down on your board, you'll see that it's got pin names all around it: A, B, decimal point, C, common, D, E, G, and F. Okay, so those represent the various segments that you see right on here. So the common is referred to right here. Is it the common anode or the common cathode? Now that kind of represents, let me just bring this right back over here, different ways of hooking up your 7-segment display. So really inside that 7-segment display, you've got, is this going to focus for me here? All right, we had that focused a little bit earlier. And so here you can see we've got 4 LEDs, and we can join them up in a couple of different ways. Common just means which side do we hook together. Okay, so we've got the anode or positive side right here, and the cathode or negative side right down here, and electricity flows from your anode down through your cathode. Okay, so we've got a choice. Do we want to hook all of our anodes up together and make it a common anode, or would we prefer to hook all of our cathodes together and make it a common cathode? Now, what difference does it make? Well, if all the anodes are hooked together, as they are in this one, what I have to do then is, in order to make an LED light up, I need to put this side down to ground so that electricity can flow through the LED, through the resistor, and then down to ground, which means that I'd have to set my Arduino pin low to turn an LED on. And if I set my Arduino pin high, that would be plus 5 volts, and that would be pushing back this way just as hard as the voltage was pushing down right here. So we'd have no current flow through right there. So setting it high would turn it off. Later on, when we're developing our patterns for the 7-segment display, we have to keep in mind whether we're dealing with a common anode or a common cathode display, because it really does make a difference. Let's just pop that right out of the side there. So we're going to start, and we're going to say common anode because that's the default one. And we've got these 2 common pins right here. So what I'm going to do is I am just going to come along and connect that common pin. That doesn't seem to be properly mounted. There we go. Make sure it latches in and they've got a good grip so that this one right here, when I light that up, is right there. And we'll just take that over to the red line right there and make sure if we're connecting to the red line that we make it red. And so there, a common one is all hooked together. And let's see if we can turn segment A on by hooking that up to a black line right there. Make that black because it's going to go around. And let's start our simulation and boom! Okay, apparently we're putting 21,600 amps through there according to this simulation because we have no resistance in there. I think 21,000 amps would have blown up our breadboard computer and probably half your house in the process of doing that. So I'm just going to stop that simulation right there and get rid of that black line because we need a resistor. Okay, so let's grab a resistor off of our list. I scrolled up, it's the very first component. Bring it right to there, and then there's this rotate button up here, or you can just hit the R key and rotate it to 90 degrees. Let's bring that in and pop it in right there. And now we can try hooking this line up to ground and start the simulation. There you go. You can see that segment A is turned on when we hit this straight down to ground. Okay, working great. I'm just going to stop that simulation. Let's come in here. If you click on that resistor, okay, right clicking doesn't give you the copy and paste command, but you can come in here and I can't remember if there's a command right along the top here or not. Copy, there you go. Control C works as well, but when you've got it highlighted, hit copy, and there's your paste. Control V works for that as well. I'll be using Control C and Control V a lot, but if that's not working on your computer, there it is right up there, and I can paste that in. Now I want one coming off right here, and we can check that out. Let's just add another line, put that into ground, start our simulation. Look at that. Now we've got two parts of it turned on. Now, obviously we've got the Arduino here for a reason. So let's take these lines and instead of using just wires to control them, we're going to use our Arduino to control them. So this is segment A. So from right here, I'm going to come off the board, come down here. No sense wiring nicely onto the board. And I'm going to hook A around right into here and hook that into port 7. And I'm going to use a color other than black because that's not going to ground. And then this one right here is B, and I'm going to hook B up to 6. And again, I'm going to give that its own color. Now, you're probably looking, I could just draw a straight line right across there. By the time we're done, there's going to be lots of wires on here, and it's going to be looking a little bit messy. So there we go. We've got those routed. So 7 will go to A, and 6 will go to B. And now let's take a look at our code. We should be able to come in here. I'm going to get rid of this chunk of code, and let's just try this out by saying we will set pin, no, not the built-in LED, set pin 7 to high, duplicate, set pin 7 to high, set pin 7 to low. Let's add some delays in here. There we go. Now we have a blinking segment A. And I can stop that simulation. I can come down here. I can take all this code. I can go duplicate that code, tuck it in underneath, and I'll set 6. Now, this is interesting. What's going on? They're both on at the same time. Well, you'll recall that what we did here was we finished off by setting it low. Although normally low means something's off. What it means here is that the Arduino pin is in the low state. So when we set this high, it turns the segment off, and when we set it low, it turns it on. Remember, we're dealing with a common anode LED right here. Okay, if we were dealing with a common cathode, it would be the other way around, and we'd have to provide power from the Arduino through here down to ground. This way the power comes in here, and the only way it can get out is when the Arduino pin is set to low or 0, because that's the equivalent of tying that pin right down to ground on the Arduino. So our electricity needs to come into the board from the Arduino up through here, down through here, and now it needs a path back to the Arduino. And to get that path, we need to set that pin low. So let's change this up a little bit. So what we're going to do is we're going to set this low, okay? That will turn it on. Then we're going to set it high. That will turn it off. We're going to set this low. That will turn it on. High will turn it off. A little bit inverted from what we regularly see. Okay, let's start the simulation. There's one on, there's A, there's B. A, and then B. Great. We've got A and B tested, and they seem to be working. Now, follow along on here because we are going to use this for some of our binary number magic that we're going to do a little bit later on. Okay, we're in here, and I'm just going to use the Control V command again to make sure that I get another resistor, and I'm going to find C. That one's C, I believe. Let's double check. There's C, and then I am going to take that from C, and I am going to run a line right here, out over here. Oh, I guess I can come right to here is going to be fine. Down in here, I hope I left myself enough room to do this nicely. I'm going to put C into pin 5. So A, B, C. All right. And let's start our simulation here. Oh, stop the simulation. Let's bring our code back up. And let's see if I change that to pin 5. Do I get a blinking C segment? There we go. There we go. Now, I'm going to stop the simulation. Notice when it starts up that they both start out on. See, they're both on, and they stay on until I set that high. Okay, that's because when you start your Arduino, the default state for all of these pins is to be an input. But as soon as they're set to be an output, their default state is low. So if you want something to start out high, you have to tell it that right at the beginning of the program. And we'll do that when we get into our code. Okay, so we've got A, B, and C in there. I'm going to stop the simulation. Now I've skipped over decimal point right here. Okay, we'll come back and do decimal point later. There's A, B, C. Where is D? Okay, let's give D a resistor. Okay, that one is D, and let's see, D is going to come down here to pin 4, so we'll come off over here. There we go, and we'll give that its own color. And there's E, and let's bring a resistor in to pin E. Okay, very important that you get these all matched up and you put them in the right holes. And the little green highlighting there really helps you figure out what you're connecting to. We'll bring that down over here. And we'll put that down. There we go. And let's turquoise. There we go. So now we've got D and E turned on. And if we want to test that, we pop over to our code and let's just change this to, that should be pins 4 and 3. Now, you'll see what I'm doing is testing this as I go along. Okay, and that's one of the things that I like to do when I'm setting things up, because it's really simple to troubleshoot one or two little things that you've done to the board and say, oh, I got those in the wrong order, I've got the wrong sequence. But it gets a lot more complex if you've got to come back later on and troubleshoot a whole bunch of things. Okay, and so we go all around that way, and now we've just got a couple segments left to do. Let's stop our simulation. And let's finish this off with a couple more resistors. This one is going to go in right here. And that's going to be F. So let's hook up F from that line right out there. It's going to come into pin 2. And we'll give it a unique color. And then we'll hook up pin G, and then we'll do the decimal point. Oh, there we go. There's pin G. Okay, now we've got those all hooked up. And finally, just for completeness, you can see we've done the 7 segments here. We've got 7 resistors for each of the 7 segments that make up the number. But now we can finish it up by adding the decimal point right in here, because this one is our decimal point. And that one's going to connect right there. Come up this way. That one is just going to come right in to pin 0. Okay, now I know I've mentioned that using pins 1 and 0, we probably shouldn't do that too often unless we've got a real purpose for doing it, because pins 0 and 1 are what the computer uses to do computer communications. These TX and RX LEDs will flash on and off when data is going to and from the computer, and they go to the @mega pins that are connected to pins 0 and 1. But for the purposes of today's demonstration of binary that we'll get to in a little bit, this is a great way to go about doing it. Oh, I didn't want to move that there. I had everything all nicely lined up. Control Z fixes all that. Okay, so now we want, before we get into doing too much else, I want to see if I can display some numbers on here. So I'm going to bring some code over here, and let's start out by seeing if we can display the number 1. So if I have a little drawing right in here of our 7-segment display, and let's just take a look at that right here. We've got A right up here, which I've got hooked up to pin 7, and we've got B right over here, which is hooked up to pin 6. C right down here, which is hooked up to pin 5. D down at the bottom, hooked up to pin 4. E, which is hooked up to pin 3. F, I have no idea why I drew F so much larger than E. It's hooked up to pin 2. And G in the middle right there, which is hooked up to pin 1. And our little decimal point down here is hooked up to pin 0. And we need to turn these low in order to turn them on. So if I want to see the number 1, I need to set 6 and 5 low and everything else high. Okay, so let's take a look at how we can go about doing that. There we go. Okay, so over here, I'm going to set, well, this should be an easy one. I wanted 6 and 5 to go low. Oh, I was clicking on my other screen over there. The other screen is what I'm using to do all the recording on, and it's got a lovely representation of the current screen. It just, right, 6, I want to go low. 5, I want to go low. And then I want to turn 6 high and 5 high again, and that should make the number 1 blink on and off. There we go, 1 turns on. Those statements are 1 second apart, so I can see them going on in that sequence. That works out really great. Okay, let's stop our simulation right there. If I wanted to make the number 7, okay, well, I just have to add a couple more commands. And what I'd put in here is set pin. So that's the segment A up at the top, and that's hooked up to pin 7. So now I'm going to set 7 to low and 7 high, and now start simulation. There we go. I've got the number 7, and then you can see it being built and disappearing as it comes together right in there. And you can see that because of the way I've spaced the timing in there with the wait statements, that they don't all turn on all at once. Now, of course, they never turn on all at once because there are microseconds between each execution of a command, but we won't worry about that. You can see if we wanted to display the number 8, it would just take a lot more lines going around right in here. And this is one of the places where drag and drop starts to get a little bit tedious. So what I'm going to do is say, let's break out of drag and drop for a moment. Okay, and so under your code section right here, let's stop the simulation. And instead of doing the blocks, let's just go straight to text. And we will continue. Now, it's kept our code going along right here. And because we're using pins 5, 6, and 7, the blocks coding was smart enough to know how to set those up as an output right at the beginning. We're going to take a look at a quick way to turn all of those pins to outputs. Okay, because it's kind of tedious to go and write it out step after step. Just a reminder from the last video, okay, that we have a function right here. Void setup is a function that runs once at the beginning of the program. Void just means that it's not going to return any values to anybody. It's just going to come in here and do its thing, and it's not going to provide any feedback. And the fact that there's little brackets right in there means that it's not expecting anybody to pass any information to it. The length of the function or which commands are part of that function are determined by these little squiggly brackets or ellipses right here. And good programming format has everything indented right here so that you can see what's in between the ellipses quite easily. The round brackets are very important because those wrap up all the information that's being passed to the pin mode command. The pin mode is controlling whether a pin will be an input or an output, or sometimes something we call input pull-up that we'll talk about later on. And critically, each line ends in a semicolon. So we've got void setup, that runs once at the beginning, and void loop, that runs continuously. That's a forever loop. Now, we could just go on, we could say pin mode 0, output, pin mode 1, output. Boring. What we're going to do in here is we're going to come in here and we're going to use a for loop. A lot more efficient once you understand how the for loop works. Starts out by typing 4. Now you'll notice that we got it right because 4 changes color. Okay, and then we put a bracket on there, and I have to declare a variable. We'll talk more about the variable types, but for right now we're just going to use an int or integer variable type. It's our most common one in the Arduino. For int, and I'm just going to say x equals 0. Now, that means that I'm going to have a variable called x that exists just for this loop, and it's going to start off at 0, and I want it to go so long as x is less than 8. Okay, now that means this loop won't execute when x equals 8, because 8 is not less than 8. 8 is equal to 8. Okay, so this is going to go 0, 1, 2, 3, 4, 5, 6, 7. Now, how do we know it's going to count by 1? Well, in our last video, I showed you how to say x equals x plus 1. Okay, now that works fine, and we take whatever's in x and we add 1 to it. So we take a look at x. If 0's in there, we add 1. Now we've got 1. If 1's in there, now we add 1. We've got 2. This happens so much that there is a simplified way to say that. X plus plus. Okay, in other words, just add 1 to x. It's because we use it so much that that is a common way of doing it. I think I need to put a semicolon in right there too. Okay, wrap that up in brackets because those round brackets say that this is what controls the function. And then we say how long is that function going to be. And this is like those two orange arms that wrap a loop. So just go ahead and create them right there. And now everything that's in between those two is indented a little bit. And now we can just say pin mode x, comma, output. So when the computer starts up, okay, the Arduino starts running, it's going to come in here. First thing it's going to do, it's going to create a little variable called x. It's going to put a value of 0 in it, and it's going to loop through this code 8 times, setting pins 0 through 7 to be outputs. Now, as I was saying, the default mode for all of the pins when they start an output is to be low. We want to start them high so that the LED will be off. Let's take a look at what happens if we don't do that. Oh, what does the error function say? The error statements are your friend. We get all sorts of errors. In function void setup, expect bracket before semicolon token. I didn't need that semicolon in there. It's only at the end of long lines that we need that. There we go. See how they all turn on right there? Okay, and now sometimes some of them are turning off. Well, that's because all of these are outputs, meaning that they're all low. And their default state is low. We need to change that default state, and we can do that by taking this code. Actually, we don't even have to take that code. Add one more line to it and say digital write x, comma high. And so now we come through and one pin at a time, we set them each low, and then we set their state to be high. Now it starts out, and our 7 is appearing right in here. Great. Okay, let's take care of some of this right here. And let's see if we can make, I'm going to stop the simulation before I can do any code editing. Let's come in here, highlight this code. Okay, now we've got nothing in there. And let's see if we can make the number 3 display. Okay. Let's do 2 because that uses something over on this side right in here. So for the number 2, we're going to have A displayed. So we have to come in here and digital write. Okay, then we're going to say 7, comma, low, and that will set on pin A. Then we'll go digital write. B has to be low for this one, so that's 6, comma. Then we'll go digital write. Okay, now we need to think a little bit right here because we've got A, B. This one right here is G. Okay, so if we want G on, you've got to find the G output right here and say, where was G hooked up again? It's that purple line that comes down to pin 1. Okay, and then we need this one right in here. This was going to be E, needs to be on. E is hooked up to terminal. There we go, that resistor, the blue line right there, that comes into pin 3. So we go digital write 3, comma low. And then finally, we need D to be turned on down here. Okay, and D is hooked up to this one, which hooks into the green, which is 4. Okay, let's start this code and see what happens. Hey, we've got the number 2. Can you make the number 3 appear? Give it a shot. Tell you what, why don't we both press pause and you see if you can make the number 3 appear. Can you make it go 2, 3, 2, 3, 2, 3, 2, 3? I'll do the same thing, but I'm going to hit my pause button on the recording while you hit your pause and you try it. Well, how'd you do? I've got my 2 and my 3 displaying here, blinking back and forth, but there were a few tricky little steps in there that if you figured them out on your own, pat on the back, you probably had to fight through this a little bit and find some nasty little tricks. One of the things that's a little bit nasty in there is that you need to put a delay in here or else you don't see the change because the microcontroller runs so fast. If I didn't have this delay statement in here, let me just comment that out and take a look at what you'd see. Without my delays, you'd see a blurred thing like that. Now, these are actually turning on and off. You can see that some of them are a little bit dim. Okay, that's because they're turning on and off really fast. But to our eye, it looks like they're on all the time. So to show you that, all I did was added //. That's called commenting out a command. And so right up here, you can see I've put comment codes in here to say that this is going to display the number 2 right here. And that this function then comes along and clears the display. Because if I don't clear the display, let's get rid of this right here. Again, I'm just commenting that out. I'll get rid of that later on. But if I don't clear the display, I'll turn something on. And then it never goes away and it stays there. Okay, so if you got the delay and you got the clearing of the display all set up, then that's great. Okay, very happy for you. And you've got the number 2 and 3 displaying on there, and you're giving yourself double pats on the back for getting both of those little tricky parts worked out. Okay, good for you. You're getting the hang of this. Now, while you were doing it, if you've got the clear to the display all worked out right in here, you're probably also realizing that, look, I've used that code a couple of times. That would probably make a great function. So I could come down to the bottom right here and make my code go a lot easier by saying void, okay, because this function is just going to clear the display. It's not going to return anything. Okay, clear display. it's not taking anything in right here. And I can go like that and like that. So those brackets are going to control what happens in clear display. And I can take this section of code right here, cut it out, and put it right down in here. Okay, now this is outside our main loop. Okay, so now all I need to type in here is clear. And I need to put those brackets in even though I'm not sending it to it. And what will happen is my code will come to right here. Then it will jump down here. It will clear the display and it'll come back right here. So in here, I can also put clear display. And it's like having a new command all set up for clearing the display. Expected declaration before. Oh, okay, so if you see that one, let's just close that error message right there now that we've seen it. Okay, that's usually a sign that I've deleted a squiggle bracket in there. And you can see when I got rid of that chunk of code right in here, I left one of its ellipses right behind in there. So if you see that command or see that error message, then take a look at your ellipses and see what's going on right there. And if I get rid of that one, the reason that was a problem was because it came down here and seeing that closed ellipse, it matched it up with that one. Then it had another closed ellipsis and it said, what the heck is going on right there? So now the code's working the same. It's coming through here. It's turning on number 2 and then it's waiting. Then it's clearing the display. Then it's displaying the number 3. It's waiting. Then it comes down here to clear the display. So we've got a function built in there right now. Now, we could go on and we could develop digital write commands for all of the different numbers going on in there, but we can actually solve this a lot faster and a lot more efficiently using binary numbers. And I'm going to show you a place where binary numbers come in really handy. So let's just bring, excellent, my focus is still on there. That right over there, and there. Now you get a big picture of me talking as we take a look at some of what we're going to do right on here. So you'll recall that a 1 byte binary number has 8 bits to it. Okay, and this is going to come in handy because not coincidentally, very intentionally, we've got 8 bits controlling what's going on our display. So what have we got going on our display? Well, we've got A, B, C, D, E, F, and G segments plus the decimal point right there. Okay? And so we're going to take these line them up right like so, and then we're going to figure out what pattern we need to display each number. Now, this is the equivalent of the 0 byte bit, and so this is going to have a value of 0 or 1. This will have a value of 0 or 2, 0 or 4, 0 or 8, 16, 32, 64, and 128 in decimal. Okay, so if I want to display the number 0, okay, that's going to be, I'm going to need to set A, B, C. All of these are going to go low. Remember, low actually turns the LED on. Okay, A, B, C, D will be low. E will be low. F will be low because we want it to be on. The only one that will be off will be G and the decimal point. if I take this as a binary number, an 8-bit byte, and I add that up, then I've got the 1 bit is on and the 2 bit is on, and that equals 3 in decimal. If I want to display a 1, okay, so 1 is just going to be the A will be off, B will be on, and C will be on. And now I set this to turn everybody else off. And if I add that up, that's 1, plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31, plus 128 is 159. Did I get that right? Okay, now that's all well and good. You can see how that math's coming together, but why does that matter to me? Well, that's because each of the status of each of our pins is also a bit called port D. Okay, now there's other ports on the Arduino for dealing with some of the other pins that we've got on there. But if we were to take a look at port D, and it's got 8 pins on it, 0 through 7. Okay, so 7 is 6, 5, 4, 3, 2, 1, and pin 0. 7 is controlled by the 128 bit, the highest order bit. 6 is controlled by the 64 bit, and this is controlled by the 32 bit. So we can take this number right here, and if I pump that into port D, then my pins will go, let's see, so 159, that will go high, low, low, high, 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 and high, because this binary number will plug into right there, and each of the pins is represented by 1 bit in that byte. Okay, so I've got 2 numbers right here for 0 and for 1, and we can use those by saying port D equals something, and that's going to save us a whole bunch of coding as we go along. It's going to get kind of fancy pretty quick, but it's a nice application of your binary numbers. Let me just shrink some of this back down. I'll drag that off the code and throw it in the top right there so that we can keep track of that 3. And let's take a look right in here. And right, don't click on the don't click on the OBS Studio screen. So what we're going to do is we're going to get rid of this chunk right in here. Okay, and I am going to say port D equals 3. Now I can add my comment in right here, and I can say display a number 0. Now the computer doesn't care if I put a comment in there. That's just helpful for people who are looking at it. Now instead of doing all those digital rights in there, port D equals 159. Zero, 1, 0, 1, 0, 1. All right. Can yours go 0 and 1? Let's pause right now, and let's see if you can go through and figure out how to get all the digits 0 through 9 to appear. How would you generate the binary code for the digits 0 through 9? Oh, right. I stop the simulation and I press pause over here while I go to think about the same thing. Okay, how'd you do? Well, I'll tell you, I stopped partway through. Okay, I went 0, 1, 2, 3, 4, 5. I said, okay, I'll just loop around. And I did that so that I could check each of the numbers as I was coming along. Because if I was doing it all wrong, then what would be the point of doing it all wrong all the way up to 10? Never be afraid to stop and check small segments of your code as you're coming along. In the process of it, you may have also discovered that you don't need to use the clear display command anymore. Since you're setting every bit in here, each time you go and set that number, you're controlling all of these pins. So when you display a new number, it automatically clears the old number, which our previous code did not do. So we don't need the clear display command in here anymore. Now, you're probably also getting a little bit tired of converting from binary into decimal. And it's actually good to know that the Arduino has ways to make it a little bit easier for you. In fact, you can express your numbers directly in binary in here. So for instance, right in here, let me stop the simulation right here. Now I've calculated the bit pattern that I want for the number 6, but I could also say port D equals B, and my number 6 pattern right here goes 0, 1, 0, 0, 0, 0, 0, 1. Okay, and then I can go and putting that B at the beginning of the number should indicate that this is a binary number. Oh, so there's a B. Oh, it likes a capital B. Let's start that and see how it goes. What happened in there? 1, 2, 3, 4, 5, 6. There we go. That's working right. So now what the Arduino is doing is it's representing this number, which I calculated to be 65 based on the binary representation, and it happens to know that it can take that exactly as a bit pattern right in there. So you can also use bit patterns directly in to the Arduino. This number right here is exactly the same as 65. Let me stop my simulation and add a note right in here. So the Arduino is really good at picking up on binary, and that might save you a few steps. And sometimes you'll see bit patterns displayed that way. Sometimes you'll see them displayed in decimal. So we can do capital B, and for our bit pattern to turn on a 7 on this display, we can go 0, 0, 0, 1, 1, 1, 1, 1. Delay 1000. Ha ha ha. Now 8, as you probably noticed, is a very easy one. It's got all of the segments on, and only the decimal point is turned off in our case. So 8 is going to be equal to 1. Or in binary, now bit patterns like this and binary numbers have been important to programmers from the early days of computing. And in fact, they're still very important to everybody right now. Let's see, did our 8 work okay? Oh yeah, always nice to check that out. So because these numbers have been really important, people have tried to come up with easier ways to express them. And one of the things about doing it in decimal is that you've got to do some aspect of math to represent it. So, you know, not only that, you can end up with up to 3-digit numbers. Sometimes you get 2-digit numbers, sometimes you get 1-digit numbers, sometimes you get 3-digit numbers. But if you're trying to create a nicely formatted uh, you know, printout of what's going on inside the computer, that's a little bit of a pain. And so computer programmers came up with a better way to represent that. And they called that hexadecimal. And in the hexadecimal number system, they started out and they said, okay, this is a base 16 counting system. And what that means is that in binary, you start out at 000. Oh, I'm off the page already. Okay, and this is our ones column, this is our twos column, our fours columns, and our eights column. Okay, and in decimal, the numbers that we usually use, that's 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and if we keep going, just realize I'm using up a lot of the page here. I'm going to have 1, 0, 0, 1 will be 9, 1, 0, 1, 0 will be 10, 1, 0, 1, 1 will be 11, 1, 1, 0, 0 will be 12, 1, 1, 0, 1 will be 13, 1, 1, 1, 0 will be 14, and 1, 1, 1, 1 will be 15. Okay, and okay, that makes sense. You can figure all that out. But what they came up with was they said rather than using extra digits right in here, we're going to have hexadecimal, or often shortened to hex. And hex is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, not 10. What am I doing? It keeps it to one decimal. A, B, C, D, E, F. So those numbers that have A, B, C, D, E, and F in them are just another way of representing that. Now, what's really nice about doing it this way is that you can use any two hexadecimal numbers or two hexadecimal digits to represent any byte. So for instance, along here, okay, this number right here that we would call 11 and would require numbers to show us, 2 digits to show us, that's just represented as B. Now, where this gets really useful is when you start coming up with 8-bit numbers. And keep in mind that 8 bits gives us a byte, and it goes up to 255. But in hexadecimal, okay, when we put this together, we get F, F. Okay, so that means that I've got 15 in the 16s column, to use decimal, and 15 in the ones column right there. So that is going to give me 15 times 16 is 230. No, 15 times 16 is going to be, my mind is completely blank out here. I know what it's going to be when I add it all up. It's going to come out to 255. So I suspect that's going to come out to 240 when I do it right there. Yes, because 15 times 15, it's getting late at night. 240. just didn't seem like it should be coming out like that. 240 plus 15 gives me my 255. Now, in decimal, that would require an extra digit to display. It would take up a whole bunch of space on the page. It wouldn't print out neatly. But most usefully with this is I can take a look at any of my binary codes right here. And if I match the code up, okay, so here I've got 1001. Okay, 1001 is equal to 9. Okay, so that was 1001, and that's 1001 again. So that was 9. Notice that I'm not actually doing any math. I'm just matching things up in here. And for 6 down here, 0100, that is 4. And in here, 0001 is 1. So that would come out as 41 in hex. So I've got 2 characters to represent something, where in decimal I'm going to need 1, 2, maybe 3, but this gives me nicely formatted output, and it allows me to translate a bit pattern into something a bit more compact without having to go through and doing a bunch of math. And so you'll see hexadecimal used quite a bit. So I've got the ability to take these bit patterns and translate them into hexadecimal. And that would be represented as 0x and then the digits that represent that. So one of the things that I came along and did in here was I said I can represent this code in a couple of different ways. So for instance, for the number 7, okay, we can say port D equals, and if I take a look over here at what my number 7 looks like, that's 0001, and 0001 is, of course, 1 in either hex or decimal, and 1111. So instead of having to type that all in binary, I can say 0, and helps if I put that up on the screen. So 0001 for code 7, 1111 coming all the way along here. So that's a 1 and then an F in binary, or in hexadecimal, to show that 7. And so I can say 0x, small x, which is our code word for everything that comes after here is going to be in binary, 1F, capital F. Okay, that should display my 7, delay 1000, and then I can say port D equals, well, doesn't matter what character number you use for 8. 8 is an easy one. Let's use decimal because it comes all the way over there, and all we're doing is keeping the decimal point from turning on. And port D equals, oh, what's our next one for 9? 0001, so that's a 1. And then when we come along there, that's the 8-bit on, and that's the 1-bit on. So that is going to be a 9 in hexadecimal. So we've got 19, so 0x19. Delay. And now this should pop up and show our simulation in here. And now we've got this 7-segment display counting to 9. And you're wondering, really? Do they have to do this all the time? And this is actually what's being done all the time. Anytime you look at a 7-segment display, this code, or some variation of it, is being used to figure out which digits go on, because you're just turning segments on and off. Now, if you've got a 4-digit display, say you want to be able to count up to 1,000 or display the time, then what you need to do is you need to be able to turn this one on really fast, then this one on, then this one on, then this one on, and you actually use these same 4 pins, but you just spread that across 4 by blinking the displays really, really fast so that humans can't see. It's a little more efficient way to go about doing things. In fact, a lot of displays are set up to take advantage of the fact that our eyes are very slow to respond to things. Now, so this is much more efficient coding than what we would have been doing with digital write, and we're able to do it all because of binary. And we can express things in decimal, binary, or hexadecimal. The computer doesn't care. They're all the same number to it. In fact, there's one more thing we can do to make it even a little bit more efficient. Now stop the simulation right here and make a few changes. And what I've done is I've taken all of the values from down here, 3, 159, 37, and put them along right in here in something called an array. And an array lets me hold multiple buckets right in here and then address them individually. So if I wanted the third element of that array, I'd get 37. If I wanted the fifth element, it would come in here, 1, 2, 3, 4, 5, and I get 153. This is a byte-sized variable, which is one of the variable types available in Arduino. We'll talk more about them in just a moment, and then that'll be it. So what we can do with this now is instead of having to go through and display these one after the other, I can take all of that because I've got the data from each of those commands and I've tested everything right there. I can get rid of that, and I can get rid of my clear display command because I don't need that anymore, because using the binary numbers and the port commands, I just overwrite that port. I can come in here and I can say for int x equals 0, x less than 10, okay, so 0 through 9, x plus plus, so x is going to increase incrementally by 1 each time out. Now I'm going to say port D equals sev seg. I could have called it anything, okay? And then this is where the square brackets come in. They allow me to access the elements of an array. So the first time out, it'll be sev seg 0, which will be 3. The next time it'll be sev seg 1, so it'll come and find the 159. And then I'll put a delay in here of 1,000. And there we go. This loop will run here. And this, oh, what did I forget to do up there? Oh, I used the wrong bracket up here. I started with an ellipses. 19. There we go. Need to finish with an ellipses. They always need to match. And down here I deleted one extra ellipses. So if you start running into problems like that, don't get too panicked. Follow the error messages. Look for matching brackets. Make sure you've got matching brackets. We all mess it up. And here we go. It's counting because it's coming along and going, okay, find me that number first and display that number. Find me that number next and display that number. It doesn't know it's displaying that number. It's just lighting up a bit pattern, but it happens to be a bit pattern that we've made intentionally to match our display. And if you've done that, you're doing better than ChatGPT did, because I tried getting ChatGPT to write this code earlier, and it took a lot of prompting to get it even close. And it was still getting things a little wonky. Alrighty. The last thing I need to conclude is what were these variable types that we were looking at. So you see I've referred to this one as a byte variable type. Okay. You just pause this right here. We don't need it counting anymore. And you can find more information on all of the variable types by Googling Arduino reference. And this has the whole language reference for the Arduino. And you can come in here and each of these is alive. And if you scroll down here under variables, you'll find data types. And there's your byte variable type. So you can come in here and take a look. And it just says it stores an 8-bit unsigned number from 0 to 255. Okay, so great. That's exactly what we've been doing with it. We want it to store a number from 0 to 255, or in hexadecimal from 0 to FF, or in binary from 0 to 11111111. I think I got enough ones in there. Okay, so that's one way to store a variable, and it's very similar to a type of variable called the unsigned character variable type. Okay, so a byte variable type and an unsigned char are actually the exact same thing. Now, what the unsigned means, positive numbers only. So if you just go to a regular char variable, it's still going to have a maximum of 255 different values and occupy um, a, a byte of memory, 8 bits of memory. However, this can actually represent numbers from minus, I always get this wrong, minus 127 to 128, no, minus 128 to plus 127, I believe. But 255 different values can be represented there. And this got its name because this data type was typically used for storing characters. So we used a byte to store a bit pattern that would display a number. But in your computer, you need to use bytes and bit patterns to represent characters. And to do that, the traditional way of doing it was to use something called the ASCII character code, American Standard Code for Information Interchange. And the ASCII code has been around for a long, long time. And so you're using the same ASCII code as I used when I was learning programming. And somewhere down here, it's got a table that shows everything that's stored in here. Now, what's kind of cool is that ASCII includes more than just numbers and letters. It's got your capital letters, it's got your punctuation marks, but it also has some control codes. So for instance, when we send that print line statement and the Arduino creates a new line on the serial monitor, we're actually sending character code 0001010 or 0A or decimal 10 right in there. Okay, and the carriage return, which it explains on here, okay, sets it back to the beginning of the line of text. So that is ASCII character code 13. So all of those little controls that move something around on your keyboard are represented right in here. And sometimes they've got this carré notation, which is sometimes the control code that it's used to generate that character because it doesn't show up on your keyboard. So ASCII is kind of neat. It's also got printable characters, and here's the binary code, well, we don't use octal anymore very much. That's base 8, your decimal code, and your hexadecimal code for all the different characters that you can represent in the ASCII character set. And this is a neat way of representing them on a chart that has them laid out in hexadecimal style. So this is the first digit in the hex. Here's the second digit. And another reason why it's neat to do it in hexadecimal is this little chart. E comes along in here. 4 is the first digit. 5 is the second digit. And so hexadecimal 45 shows the letter E. Comes in useful later when we're trying to display characters. Now, of course, you've got way more characters on your cell phone now, because if you scroll down to the bottom here, you'll realize that we were using 7 and 8-bit codes back in the day, but along came Unicode, and somebody said, hey, all of our smartphones are able to handle way more data than we used to be able to. What are we going to do? We're going to generate a 16-bit character set, which can store 255 times as much data as an 8-bit character set. So now there's like over 65,000 different characters, and so you can make a smiley character or a frowny character. It takes a while to fill up 65,000 characters, even with international alphabets included in the new character set. So that's the char and the byte. They're kind of interchangeable, and well, char not so much, but the unsigned char and the byte are exactly interchangeable. Now, they only go up to 255, so we use ints a lot too. because it's kind of the generic data type on the Arduino. And on the Arduino Uno, which we're using, it stores a 2-byte value. Okay, and that's going to give us a range of 32,000 to 32,000. If you put a number outside of that, you're going to run into problems. We'll take a look at some of those problems later on. We've been going for a while today. But if you do run into those problems, you can switch to a long variable type. And the long variable type uses 4 bytes and is a 32-bit variable that can go from minus 2 billion to plus 2 billion. And if you use an unsigned long byte, it won't use the negative numbers, so you'll be able to take that up to close to 5 billion. Well, 4.3 billion anyway. So we're going to use some of these variable types. If you need decimal points, however, none of those variable types will help you out at all because they don't handle decimal points well. That's where the floating decimal variable type comes in. Okay, and they store this by representing the number as a mantissa and an exponent. So in other words, a certain number raised to a certain power. So they take 4 bytes to store, but they take a long time for the computer to process, and they don't store the number precisely. If you store the number in an integer variable type, then you store that number exactly and you can't get it wrong. Here they have to round off and settle for close enough. Most of the time, close enough is good enough, but there have been a few famous errors where rounding errors have caused problems. Anyway, I'm not going to delve into that too much, but there's those variable types. That's what the bytes and ints that we were talking about are all about. And you've learned a little bit about hexadecimal and binary numbers. And maybe now you know why dead beef is worth more than a bad babe. Thanks very much. Talk to you soon.